Joaquin Turiaci, who's visiting us from the IIS, but as you see, he'll also be soon moving to University of Washington this fall, and he's going to tell us about black hole, spin, and statistics.
Okay, thank you very much for the invitation to give a talk here. Okay, so there we go. Okay, so the conceptually the idea behind this line of research I will talk about is based on this central dogma or holography, which is that black holes can be described by a quantum system for an outside observer. So this is a picture where you can see the black hole and some quantum system that is supposed to reproduce the black hole, and this is a conjecture, and part of the research that we're doing is to try to test it and understand when it's true and why. But anyhow, the most basic question we can ask is what is the number of degrees of freedom of this quantum system? The Wittgenstein-Hawking entropy provides the cursor prediction, telling you that the number of states, well, the degrees of freedom, the number of degrees of freedom is of order of the area over 4G Newton, or the dimension of the Hilbert space is exponential in this quantity. And the purpose of this talk will be to study how to compute using gravity how many of these states are bosonic or fermionic. So I will try to explain that in this talk. Okay, well, what is the framework that I have in mind? So we're going to follow an approach that seems to have worked in all examples that I know of most of examples, well, maybe not all, but examples from holography, concretely from ADS-CFT, which instructs us to, so we decide what quantity we want to compute of this quantum system, for example, the partition function, and then Wittgenstein-Hawking tells us to perform the gravity path integral with these boundary conditions over all smooth geometries that satisfy the boundary conditions appropriate to compute the quantity that you want, the dual description. So in the case of the partition function, you want the boundary to be, okay, so this would be whatever spatial dimensions you have, and then time to be periodically identified in Euclidean signature. And this is Euclidean because we're asking the Euclidean question of what is the partition function. In this case, the black hole has this cigar shape where the time circle contracts at the horizon and the spatial dimensions remain large. At least they don't contract. And this gives us a semiclassical expansion of this partition function from gravity. So in principle, it's the sum over saddles, where each saddle has its action and its one loop determinants. And the leading classical action is, if you include higher derivative corrections, gives the Wittgenstein-Hawking or the Wald improvement that I wrote down before. And then the one loop corrections are they're usually ignored or assumed to be not important, but they will be important at some point in this talk. And then you sum over saddles. And the leading one, when it is the black hole, then it gives this prediction for the number of states of the quantum system. Okay. So attempts to test this in string theory, successful attempts use D-branes that at weak coupling you can see what is the quantum system that lives on those D-branes, and then they don't compute the degeneracy, but they compute the number of the index, which is the trace weighted with a -1 to the f. So it's weights bosons and fermions with different signs. And it is this index which can be extrapolated from weak coupling, where we can compute it, to strong coupling, where it's described in a black hole, where we would think we can compute it in gravity, but not easily from quantum mechanics. And this has been successful because people compute the index, they take the limit of large charges, where the black hole that becomes a strong coupling is large, so you can trust semiclassical gravity, and then it matches with the area of the black hole. But a small subtlety that was never, I don't think it was fully addressed before, is that, so in the gravity description you can compute the degeneracy using this Euclidean black hole, but you don't really know how to compute, that would be the point of the talk, how to compute the index using the Gibbons-Hawking type prescription. Partly because, okay, you can, if you interpret the -1 to the f as making fermions periodic, then naively you would think, this is not the right conclusion, but naively you would think that the black hole, since the time is contractible, cannot have periodic fermions, and then you will not include this saddle. And if that's your point of view, then what did Strominger, Baffa, and follow-ups do if there is no really classical calculation that matches the index?
So what's the caveat then? Because naively it seems a good argument, right? Because locally you would say it has to be.
Yeah, that will be the point of the first part of the talk. So maybe I will say it and then we can discuss it. Yeah, and in quantum mechanics or QFT, depending on the dimensionality, you know how to compute the index, but you don't know how to compute the degeneracy because you need to solve this strongly interacting quantum system, and in principle, in general, you don't know how. Maybe there are some special cases. But actually, I don't know any. But they usually compute the index. Okay. Another assumption that was never really addressed is the decoupling of the black hole degrees of freedom. And I'm not. This is not going to be the main point of the talk, but I wanted to mention it. The decoupling of the degrees of freedom of the black hole with the environment. So when you're counting states, are you counting the states of the black hole or some kind of a ground state between the black hole degrees of freedom and the environment? For example, in ADS, there is not really a canonical way to separate the entropy contribution of the black hole per se from the rest of ADS. You just compute the entropy of the CFT, and that in principle can include counting states with things going on outside of the black hole. So anyways, this some arguments, maybe I shouldn't say result, but some arguments explaining this recently show that perturbative quantum gravity effects, these one loop effects that I mentioned, reveal the presence of a gap in the spectrum. But this is another story I'm not going to try to motivate this time. But the idea is that you can see gaps in the spectrum near. Okay, so here we are talking about supersymmetric black holes, so they are extremal. And then you can ask what is the gap to the first non-extremal black hole. It's difficult to imagine this separation of the Hilbert space of the black hole and the environment if your gap is small. In particular, in general, you expect it to be exponentially small in the entropy. But in supersymmetric black holes, actually the gap is power law suppressed, so it's a perturbative effect. So okay, this is important. Where here S is the entropy and alpha is some other one number that depends on the details. So this is important also for those tests to be meaningful. Okay, so in the first part, to answer the previous question, I will explain how to generalize this Gibbons-Hawking recipe to compute the index. So at least now we have, so we still don't know how to compute the degeneracy, but at least we know how to compute the index from both gravity and quantum mechanics, and now it's something you can really compare. Of course, we will get the right answer, but I think it's good to know exactly how to do it. And so this is based on a paper with Luca Eliesu and Murat Kologlu, and it's based on similar ideas in different contexts, especially starting with the paper of Samir Murthy and collaborators. So in the next part of the talk, in the second part of the talk, I will extend this idea to non-supersymmetric theories, because in non-supersymmetric theories, you can still ask the question of what is the difference between, you have a Schwarschild black hole in flat space, let's say, you can ask what is the difference between the number of bosonic and fermionic black holes. So you can still compute things like trace of -1 to the f over some sector of the theory, like let's say you fix the energy of the mass of the black hole. And this is something that is tricky because classically the angular momentum is of order 1 over g Newton. Classically you don't really have access to order 1 changes in the angular momentum. So yeah, so for that reason it's not obvious how to do the calculation, but okay, I will describe it later. And this is based on a work in progress with Yiming Chen, student at Princeton, and Juan Anderson. Okay, so is there any question about the motivation? Okay. So I will describe how to compute this index with gravity. I will start with the supersymmetric case because it will be the case more familiar with the test of string theory. So I will consider a 4-dimensional n equals 2 supergravity in flat space. The field of the supergravity multiplets is just the metric, a graviphoton and a gravitino. That's the action. And there is a local supersymmetry that acts on the gravitino in this way. This theory has Reisser-Nordstrom or Kerr-Newman imperial rotation as classical solutions. We'll be interested in doing the Euclidean path integral that counts these states. And there is a small subtlety here that I'm not going to go over in the talk, but I can discuss. If you have this theory coupled to vector multiplets, depending on the boundary condition of the scalars of the vector multiplets, those scalars can run or not. Then you have this thing called the attractor mechanism. And when those scalars run, then the geometry is not Reisser-Nordstrom for a charged black hole, but it has some back reaction from the running of those scalars. In general, if you set the asymptotic value to the attractor value, you can freeze this, the scalars become constant all throughout the geometry, and then the solution is Reisser-Nordstrom or Kerr-Newman. So I will imagine that I simplified it that way, but similar story can be done in the presence of vector multiplets.
And you don't have hypermultiplets.
You can have. I don't think they affect what I'm going to say.
There was also a problem of extending them off shell.
Oh. Well, I'm not going to discuss localization, so I don't necessarily need off-shell realized supersymmetry. Yeah. Okay. So let me try to explain it in detail, even though maybe some things are probably very familiar to some of you. So the path integral we want to do has as boundary conditions. Again, we have at large r, so r is the radial distance. We have a thermal circle that I call TE that is periodically identified, and we have theta phi parameters the sphere that are the coordinates of the horizon. And in general, if we want to turn on angular velocity omega, what it means from the boundary conditions point of view is that we want fields to be periodic or anti-periodic with respect to this, with respect to this identification. So as you go around the Euclidean time, you also rotate a little bit in phi, which is the one of the angular coordinates in the sphere. But if you want the metric to be real in Euclidean, then this omega will be imaginary. And if you want the metric to be real in Lorentzian, then that omega will be real. And then in Euclidean symmetry, we will do some analytic continuation. And the spin structure is chosen so that the black hole, but this I just mean the periodicity condition of the fermions, chosen so that the black hole solutions are smooth. And what that means is that when we go around the contractible circle, so this will be the contractible circle in the rotating geometry, this diagonal line, the fermions need to get a minus sign as you go around. But we can also rewrite it, that it will be useful to rewrite this in terms of what happens as they go around time only. And then when you do this shift here, you can undo it a little bit to go back to the same angular position, and then you insert this generator of rotations to undo it.
So J is
the angular momentum. Yeah, so it rotates around phi.
So it's just gamma matrices on fermions.
Yeah. Yeah, so as you go around the thermal circle, you have these twisted boundary conditions that define your angular velocity.
But I mean, the different components of the fermions have different J.
Yeah.
And here you limit to omega imaginary.
Yeah, for the application, for the index, we will take omega imaginary. Okay, so we expect with these boundary conditions to compute the partition function of your putative quantum system if you have one. String theory gives some examples. But okay, we want to explore to what extent this identification makes sense. The classical saddles I already mentioned are the Kerr-Newman, and here I remind you some formulas, but I'm not going to go through all the details because I'm sure you're all familiar with this metric. But I'm going to write all the parameters as function of the temperature, the angular velocity, and the charge, and those are the quantities that I'm fixing. So in particular, the mass, or this usual parameter A that is identified with J, is determined in terms of omega and beta. Yeah, omega and beta. Okay. Something important.
So A will be imaginary.
Yeah.
A will be imaginary.
Yes.
Then you can get some holes there. There's no problem with that.
No.
But it's in the external limit, you would get.
Yeah, but in the extremal limit, A is not going to be R plus. I have the formula later, no, we can look at it. Okay. Yeah, so I'm not going to show. But okay, so this is not the whole story. Something that is important is that if you have in your theory particles with half integer spin, then there are also integer value family of solutions related by 4 pi n shifts of I beta omega. So if you think of the boundary conditions in this way, at this twist, if you shift omega by 4 pi times an integer, then because the spectrum of J is half integer, then the boundary conditions on your fields will be the same. It will be undistinguishable. So you should really sum over this family of solutions as distinct saddles that satisfy the same boundary conditions. And they are different because in the bulk they are different. Even though they have the same boundary conditions, the geometry in the bulk is different. One way to see it is that the angular momentum associated to them is different, so then they back react in the metric. And usually you don't think about this because the solution with n equals 0 dominates. And one way to see it, for example, and motivated by the fact that we want to take the extremal limit, is that if you take the large beta or small temperature limit, then you can see that you get the 1 minus n squared roughly, where alpha is a convenient parameter that equivalent to the angular velocity through this relation. So for example, if you fix alpha equals 0, then always the solution with n equals 0 dominates. From the solution with n equals 0, you can get at fixed angular momentum, the thermodynamics of these black holes. For example, the mass, you get, okay, the extremal mass, that is this. So this is just I'm imagining that I'm taking large Q. This is just to make the formula simpler. I'm taking large Q and J is just a small correction. So I'm taking J to be smaller than Q. So this is an approximation of a more general formula.
To these other solutions, what if I recreate back to Gaussian signature? What is the meaning for these other solutions?
They are complex, yeah.
So they don't have immediate.
No, but they're important. They are there, and they're important to make sure that your spectrum of angular momentum is half integer. And for example, if you have a U1 gauge field, they're also important to make sure that your charges are integer. So it's not clear whether you should include them or not, but if you don't include them, then you're running into trouble with some things.
But do you have an understanding of why these saddles are picked up when you re-quotate from the contour for the Lorentzian quantum? That's what they're saying, right? When you do re-quotation, you should also sum over these saddles.
Yeah. I don't understand the Black integral contour of quantum gravity, or even if that makes sense, but presumably you will want to include something like this because you want the spectrum of chase to be there.
But there's not even like a toy example, like for example, in two-dimensional gravity, you can see.
In two-dimensional gravity, well, one toy example is, yes, in two-dimensional gravity, if you have gauge fields on coupled to JT, for example, you also have three-dimensional gravity. If you do this fairy tale expansion, these type of families of solutions are subsets of the SL2C transformations that, in that case, will make you the momentum around the.
Yeah, I understand, but
the circle
I'm asking if there's a
quantum.
way to understand in principle, like how that choice of contour, the choice of repeating saddles, come from when you rotate from the Lorentzian.
No, that I don't know.
I mean, the Hawking proposal, right, is just to the patent integral in Euclidean to begin with, and slowly get Lorentzian.
Yeah, but that's the thing that seems to work when compared to, like, for example, the fairy tale. You have to include them. So I guess I'm just exploring what are even the rules in gravity because we don't know. Yeah, for example, also if you attempt to define okay, maybe we'll do that. But yeah, we're trying to understand better what the rules are.
In Lorentzian signature, the e to the is for the patent integral, you know that this integral doesn't even make sense for a free particle in one dimension. I mean, the Wiener integral is not defined. It's always defined from analytic configurations.
Yeah. Well, yeah. Okay. Yeah, maybe what we don't understand is what the gravity description of the Hilbert space, like what are the microstates and all that. But maybe that's too much to ask for from a low energy gravity point of view. Okay. Yeah, so related to a point I made before, this sum over n is not always so innocent because all these saddles become degenerate near extremality. So if you look at the formula, so I told you that the one with n equals, imagine that alpha is equal to 0 for simplicity. The one with n equals 0 dominates, but if beta goes to infinity as it does in the extremal limit, then all these saddles have the same action. And then you really need to sum over them. And to do that, you need to know what the, it's important to know what the one loop determinants are, for example, because, and okay, in this paper, we give some argument of why the one loop determinant should behave this way as a function with n and alpha, and then if you translate it into the spectrum, then this gives you this gap that is power law suppressing the entropy that I mentioned before, where this would be the extremal state, or it gives you, or states that are not, for angular momentums whose ground state is not supersymmetric, then there is no gap and it goes to 0. And, well, presumably the gap will be exponentially small in the entropy, that's it. But it's not accessible from.
So what's the dashed line and the
Oh, the dashed line would be the classical answer. So at large energies or deviation from extremality, it grows exponentially through the corrections to the extremal area. But if you take temperature to 0, this goes to the exponential of the extremal area. So this is just showing how these quantum effects actually change the spectrum a lot at low temperatures.
So going to 0 would mean that you have only one state for this?
Yes. Yeah. Well, to this order to 0, but at least that it's not it's not exponential in 1 over G Newton, or some other one. For example, 1 would be a natural number if you don't have any symmetry. Yeah. Yeah, so this is something that was not tested in any example because it will require computing something that is not protected. But yeah, I think it, well, okay. Yeah, so this is, yeah, and this is the gap I mentioned before, and then this delta function is the number of states that the string theory counting is giving. Okay, so we want to understand this calculation with the -1 to the f. Particularly, we want to be able to compute it at any temperature. So the index should be independent of the temperature, but that should be an outcome of the calculation, not something we put in. And again, this involves integrating over periodic fermions. So the misleading approach I mentioned before would be to take the near extremal Riser-Nordstrom black hole that I draw here and declare that the fermions are periodic. But as I said, this is singular. And in particular, if you compute the action neglecting the singularity, it will be temperature dependent. Just like the classical action doesn't care what, in principle, what boundary condition you put on those fermions. Another approach that was taken by Horowitz, Hawking, and Ross a long time ago was to backhand said, okay, we start with the 0 temperature solutions, and the index should be independent of temperature anyways, and now we declare the fermions to be periodic. And now you don't have any problem because the throat is at infinite distance from the boundary, and there is no point where the time circle contracts, it just continues forever. So then this is not singular, but it has a problem that if this was the only thing in the only contribution to the path integral, then it would be inconsistent with the countings in string theory, because then the action is just because of the U1 symmetry is proportional to beta. And the entropy that you would deduce from this is 0. Actually, that was the conclusion of that paper that came like 1 year before Strominger and Buffas. So okay, so we have a smooth solution, but this cannot be the one if we want to understand these countings. Okay, and the solution to both of these issues is to add rotation. So the way we should think about this is to interpret the -1 to the f as turning on at imaginary angular velocity e to the 2 pi I. Such that the -1 to the f you interpret as implementing e to the 2 pi I j. Then for this particular value of the angular velocity, integer j give you a certain sign and half integer give you another one. So yeah, this corresponds to real metric in Euclidean signature because omega is imaginary. So the proposal is that the index should be the partition function on a rotating black hole, even if the index is supposed to compute the number of non-rotating BPS black holes.
Sorry, I'm confused, but this should work also for J very even being 0.
What
I mean, this should be working for even if there is no angular momentum.
But J is not the angular momentum. J is the angular momentum of the particles.
Yes,
Fermions and bosons, not of the black hole.
I understand. But suppose you have going back to the Reiner-Nonson case, this should work anyway.
No, because
Yeah.
there is no supersymmetry.
What do you mean by the Reiner-Nonson? I mean, here I'm doing Reiner-Nonson, but what do you mean?
So this J is the angular momentum of the particles, the fermion particles.
Fermions and bosons, whatever is. So you have supergravity, you have gravitino, graviton, scalars, fermions. This
So
J
some
is.
anti-commutators of gamma matrices for
Yes.
Yeah. Well, that's probably best defined if you put in the context of string theory, because then you look at the quantum system as you're looking at the J of those states of that different quantum mechanics. Yes, but in the given Hawking prescription, we want to turn on this omega to to implement the -1 to the f this way. Yes.
Sorry, and the claim is that calculates the index for black hole with omega equal to 0 in Minkowski signature, right? When you say calculating like index corresponding to black hole.
Well, the index is automatically, if you talk about the index, you automatically imagine a grand canonical in J.
Right, but you
Because,
started with saying, well, we can think about black hole as quantum system.
Yeah.
That's thinking in the Minkowski time, right? So we think about black holes described by some metric. So in that sense, that's a prescription to calculate index corresponding to black hole with omega equal to 0.
Oh, yes, exactly, yeah. So there are two different things. One is the Euclidean metric that computes it in the gravity, in the path integral perspective, and the other one is the metric that you will want to associate to the states.
Right, yeah, that's what I'm asking.
Yeah, the two things are different. Yeah, that's important.
And that corresponds to state, Minkowski state with omega equal to 0. Right?
Yes, it will be counting that. Yeah, so there are two different. Yeah, thank you for the question. That's important. Okay, here smoothness as the horizon is immediate. Fermions are periodic in time, but when beta omega is 2 pi, it's exactly where, as you go around the contractible circle, you did one circle a full circle in the angular coordinate. So then fermions are antiperiodic with respect to this cycle, but then they're antiperiodic also in space, because this coordinate in the sphere is contractible as well. So then these two minus cancel and you get a periodic fermion in time. So you get a smooth geometry that has periodic fermions in time. So then the solution is good because it's smooth, it satisfies the right boundary conditions, and it also gives the right action that I will mention in the next slide. So if you compute the action for this configuration, you will get this. You get minus beta q plus pi q squared. Well, the beta q is not important. You can add, you can shift your ground state energy of your system. Let's imagine we did that. We had a boundary term to remove that. So the classical action is given by pi q squared, which is the extremal area over 40 Newton. But this is a calculation done at finite temperature. So in principle, the black hole depends on the temperature, but you compute the action and it's independent of the temperature. And that's the first consistency check with the fact that it has to compute an index, because it should be, unless if you have a discrete spectrum. And moreover, it gives a non-zero answer, because that previous the metric of Hawking, Horowitz, and Ross would have given a zero answer for the action. So the solutions with this parameter have a horizon at a finite distance. So the area at the finite temperature, the area is not exactly the extremal area. The area depends on the temperature, but when you compute the action, including all terms, then the action is equal to the area at extremality. And these solutions also have m equals q, so the Killing-Spinner equation is integrable, and one can actually write the solution explicitly. And these geometries can be written. So from this perspective, you take Per Newman and you plug in these parameters, but they can also be written by something called Israel-Wilson metrics. That there were some supersymmetric metrics from people found in the 70s or 80s, and then they discarded because they were complex in Lorentzian. But here we can give it a different interpretation by what you were saying before. Okay, so Just as a comment, we need to include all solutions consistent with the boundary conditions. But if you include these shifts by this integer n, then only the solution where omega is 2 pi I over beta, that's the only one that is supersymmetric. And if you compute the action, so that will correspond in this notation to n equals 0. So you see the beta dependent term is 0 for n equals 0. But if n is different from 0, then the action does depend on the temperature. And what happens there is that the solution is not supersymmetric. So actually, if you compute the mass, it's different than the charge of those solutions. So you're putting supersymmetric boundary conditions, and there is a solution that is supersymmetric in the bulk, but there is a family of other solutions that break supersymmetry in the bulk, even though the boundary conditions are supersymmetric. And we argue that, well, this is kind of, well, this is easy to see, but we argue that the one-loop determinant on these other solutions is 0 because of the broken supersymmetry. And when we look at the one that preserves the right amount of supersymmetry, then the one-loop determinant is non-zero.
Sorry, I'm confused.
Yeah.
Coming back to my previous question, because from Minkowski point of view, we're trying to calculate index for non-supersymmetric object, right? Because it's a finite temperature black hole. So
No, it is supersymmetric. Yeah.
But you have
The solution with n equals 0, that is the one I mentioned before, that one is supersymmetric for any temperature. It's not real in Lorentzian, so you don't want to give it a Minkowski interpretation.
no, but I mean, no. So again, what is the quantum system in Lorentzian signature for which we're calculating this index? I thought that was a black hole with temperature beta.
So that's the Reisner Nostrum extremal black hole, right?
No, but if it's a Kreml, then that would be zero temperature.
Yeah, it
right?
would be zero temperature.
So that's my confusion. If beta is so in Minkowski signature, should I think about calculating index for finite temperature black hole?
Yeah, I mean you compute it. Sorry.
But then it's confusing that
Finite temperature quantum system.
Yeah.
finite temperature quantum
So
system.
if you want to talk about the Lorentzian, I would say if you want to talk about the Lorentzian calculation as counting states, then I only know how to make sense of that if you talk about the boundary quantum system, not the black hole itself, because we don't know how to define the
Black hole is
microstates.
not even a state. It's just
Well,
a geometry.
yeah.
but I'm using the language like for me, black hole is certain quantum system, right?
Yeah,
And it's some finite temperature quantum system.
Yeah.
And so
Yeah, but you cannot make sense of it in Minkowski.
no, I understand that, but it's somewhat surprising to me till the that it's leading order calculations then given by some supersymmetric saddle, even though I'm asking about some highly non-supersymmetric.
I don't
Oh,
know,
but
but always calculating index of finite temperature in any
Yeah.
quantum system, right? When you do the H theory system.
Yeah, it's just that all states except the ones you want cancel, but
Yeah, that's because it's index, right?
Yeah,
and that's why.
it's just that the way it manifests itself in the bulk is not that straightforward. But
And also, I mean, you would never even dream of dreaming of doing the calculation of the index in Minkowski space for, say, gauge theory.
No, I'm not suggesting. No,
Euclidean and impose boundary
no, that's
conditions.
not my problem. I'm
So-
okay with doing Euclidean calculation. Just was a bit.
I don't know, for instance, in gauge theory, I don't even know for a quantum mechanical system how to do the calculation with a path integral in Euclidean for the index. Right? You take one particle in 0 plus 1 dimension. You
No,
have
but
to
that's
go Euclidean,
but
right?
I was asking something. Yeah, but it's basically because index really only cares about ground state. And that's why it's so. Mhm.
Yeah, if there is a gap, yes.
yes, but that's something. Yeah, it's something automatic that even if you think about comparing at finite temperature from the boundary, you already know that everything will cancel. But that step is not manifest in the bulk. Any other question?
So the first equality, z equal 1, z1 loop equal to 0, is essentially similar to the standard argument that when you break supersymmetry, you have a Gaussian mode, and if that's a fermionic zero mode, it cancels.
This one is a little bit more subtle because some of the supersymmetry is still broken because this is a half BPS state, but okay, so
Do you have cancellation between bosonic and fermionic zero modes in that case?
Yes, well, what I was thinking whether to say or not is that there is a subtlety if you put the black hole in flat space that you have to consider not the index but the helicity supertrace.
Yeah.
Where you, from the point of view of far away, where you approximate the black hole as a particle, even the half VPS is bringing some supersymmetry, so you need to do something extra to remove those fermion zero modes. But once you do that, then this zero non-zero refers to just the contribution from the near horizon region,
I see. So
where you
there's
ignore the center of mass degrees of freedom. Yeah, that's. Okay, so the general prescription is that you take -1 to the f, you write it as some e to some charge with some imaginary value of the chemical potential. You construct all the black hole solutions consistent with this imaginary chemical potential. That again is usually, not always, but it's usually real in Euclidean space. And then you look at the one-loop determinant and try to argue that it's not zero. And the examples that were studied is well, this Reisner-Nordstrom that I mentioned. And again, it can be generalized to attractor, the pool attractor solutions in the scalar set turned on. You can also do it in ADS3 cross S3. In this case, the angular momentum is not the angular momentum in ADS3, but it's the angular momentum on S3. So if you compute the elliptic genus, you are turning on a -1 to the f, where Q is the. Well, from the point of view of ADS3, it's a SU2 gauge field, but from the point of view of ADS3 cross S3, it's rotation in DS3. And then you also have this, the original paper will consider similar story of this 116 BPS black holes in ADS5, where you need to turn on some combination of the U1 arc charge and angular momentum.
Sorry, so when you say you need, that's what people did in the past. But in light of what you discussed, why can't I just turn on the usual angular momentum as opposed to the angular momentum S3, just turn angular momentum associated with the asymptotic sphere?
You can, but then you're not computing the elliptic genus, you're computing something else.
Yeah.
Yeah, that's.
But can I run the same?
You can do the same, yeah. That's more related to the other part of the talk.
Okay.
Yeah, if I have time. I start, so I have 20 minutes, right?
Yeah.
Okay, then I should
25
have time.
minutes.
Yeah, here what I meant was if you want to compute the type of things that people compute when they talk about the elliptic genus, then you would turn on some rotation in S3. And yeah, this example of ADS5 was important because there was some confusion over the years, because in the early 2000s, Maldacena, Minwala, I remember the authors, and Raju, they computed the superconformal index of n equals 4 super young meals, and they got that it doesn't grow as the exponential of the area. And for a long time, people thought, oh, maybe there's something wrong in. But I think people were, my impression from looking at the papers is that people were confused whether the boundary calculation was wrong or whether the bulk calculation was wrong, and you don't expect to have something exponential in n squared. But at least to me, this paper verified it. And there are also other papers that did it, but this is the one that focused on the bulk calculation. Okay, so in the last part of the talk, I wanted to mention what happens if you try to do the same in theories without supersymmetry, where you can still ask what is the difference between the number of bosons and fermions, even though it's not protected in any way. So in this case, it will be more a prediction. If you do it in ADS, it will be more a prediction of some property of the CFT other than something you can practically check. Anyways, so for these VPS states that I mentioned before, until now in the supersymmetric case, something we got that was not obvious that had to be this way from the start was that the index is the same as the degeneracy, and both given by the exponential of the area, extremal area. But as far as I know, this happens in all supersymmetric examples. And almost all the VPS states in this example, this implies that most of them have the same statistics. So they're either bosons or fermions. In the case of Reisner-Nordstrom, most of them have J equals 0, so they're bosons.
So that's for close to extremality, for zero temperature black holes?
Yeah. I mean the counting supersymmetric one. So the index you can compute at any temperature you want, but the degeneracy, I mean,
The degeneracy means supersymmetric.
Yeah. But so then you can ask, okay, if you apply this to a non-supersymmetric black hole, then do we expect the trace over? I put here that trace. You can imagine that I'm fixing some microcanonical window in the energy, for example, So if I compute trace of -1 to the f, is it going to be the same as the trace of 1, roughly, what I remember the degeneracy? Are both going to be of order e to the a over 40 Newton or not? And I don't have any expectation a priori because I don't know how to compute either in a non-supersymmetric theory, like from the quantum mechanical perspective. But having all states have the same statistics seems to me to fine-tune unless you have a symmetry argument like supersymmetry.
Sorry, but why supersymmetry provides a symmetry argument for that?
Well, not symmetry, but for example, in supersymmetry, in the cases you compute, you can compute that with coupling and extrapolate. So if you find that it's that if you find that the index is large at weak coupling, then you can extrapolate and you know that it will still be large because it's independent of the coupling. Yeah, maybe I didn't mean the symmetry, but the implications of supersymmetry. Of course, you can also have a system where you compute the index and it's 0, but then you imagine that that doesn't describe black hole because you wouldn't.
And this trace is computed at small temperature, or
I would describe the calculation in macrocanonical. So you fix. I will not talk about one loop determinants. I'll just talk about the classical calculation in this part. You can imagine that you do it at the fixed mass, and then the details of how you fix that window of. So you cannot literally fix the mass. You need to fix some window of energy of masses. That detail will not be important for the calculation. So just imagine that here I will talk about macrocanonical. Yeah. So if you have supersymmetry, if you compute the index, you will at least expect that to grow as into the area. So then that guarantees that you will have the same strong coupling. That's what I meant. But again, if you don't have supersymmetry, then you don't know if anything could happen. And having them all have the same statistics is a little unnatural to me.
Well, but on the other hand, it sounds even more natural that the number of bosons and fermions will be the same with exponential precision, right? Because that would require would need to change the answer, right? So that you should have the same number of fermionic and bosonic states with exponential precision. That sounds harder to arrange than most of them to have the same statistics. So
okay, that's fair, I guess. Okay, let me explain the calculation and yeah. Well, yeah. I guess that's what I mean by I don't have a proof of why. I mean, I just let me continue. Okay. Now consider Schwarschild black hole in 4 dimensions in flat space, so it's non-rotating. Then we can compute the entropy using Hawking again, and for simplicity we consider state of fixed m. Then the partition function is exponential in the entropy, that for Schwarschild is 4 pi times the mass squared. Here I'm always working at G Newton equals 1, hopefully it will be here. So we want to ask what is the difference between bosonic and fermionic. This comes from evaluating the action of a Euclidean. This calculation of the partition of the degeneracy comes from the Euclidean Schwarzschild black holes with appropriate boundary terms to fix the mass. And as I said before, at this level of the calculation, the details of how we determine an energy window are not important. We can also do it at fixed temperatures. So we can use the same trick as before, now involving a curved black hole and
when you fix the mass, essentially, you have a time integral Euclidean time that fixes the temperature. Then you add the term as beta m, and then you.
Yeah, that's the boundary. From gravity, that's a boundary term. From that perspective, you are doing the Laplace transform. Yeah.
And you, even if there are some i's in the Laplace transform, like that.
I don't think I neglected it. I think you just put them in the right place, and you get the right answer.
Because of the partition function, isn't it? I mean, system is unstable, right?
Oh, yeah. This is just a toy model, of course, because I don't know. Yeah, ideally you will work. Okay, I was mentioning this one because it's the simplest, but for example, I will also mention the most well-defined case would be to do it in ADS. Yeah, this is a toy model in that sense, where I'm ignoring those subtleties. Thank you. Yeah, the calculation in ADS looks more complicated, so that's why I picked the flat space case. Okay, so to leading order, all the states that you're looking at have j equals 0. So it's not clear a priori what the answer should be. And from this Gibbs-Hawking prescription, we need to find a solution with this value of the Euclidean angular velocity. And again, now it's just the curved black hole because we don't have any charge. So we just need to add some rotation to compute this quantity. And here I put the parameters of this curved black hole. So this is the similar as before, but without the charge. And the -1 to the f limit is to take a over r plus to go to I, so is this. Actually, okay, so in this case, I forgot about it. So in this case, you do have the subtlety that Gaston was mentioning. This doesn't happen in the charge case because a is not I times r plus, but there is a term that goes like q that guarantees that there are no funny things going on. But when you turn off the charge, then a goes to I times r plus, and then this mask has a factor of 1 plus this zeta squared times r plus. So then there is something funny here that if you want to fix the mass, then you need to scale, and this is partly why the calculation is better defined in microcanonical. If you want to keep the mass fixed, you need to also scale r plus to infinity as you send zeta to I, so that this product has a finite value. So this is a funny limit, but something we checked is that the curvature invariants are finite, so we expect that even though it's sending r plus to infinity, it's a solution with finite charges and finite action, and there is no singularity, so should be everything should be fine.
So the question would be the same as taking a limit in which a also goes to infinity or something like that.
Yeah, they're both going to infinity. Well, we computed r square, which I think in Euclidean signature, in the metric is zero in Euclidean signature, and r square infinite, then you should be good, and that's the case. But yeah. So this is a final limit. But if you do it in ADS, the formulas are more complicated, but if you do it in ADS, then it doesn't happen. Then you don't have to take any limit like this. But okay, then you can compute the action of this saddle and you get 2 pi m squared. And again, the action has an area term, but also has a beta omega j that comes from a boundary term. and the sum is, the total action is 2 pi m squared. So we get, so the final answer is this. The general is of order e to the s, and the index is e to the s over 2. That's the, and the high energy states that describe this black hole are to leading order, randomly distributed between bosonic and fermionic. So that's the way we interpret that, very related to what you were asking about what the expectation should be. So here, if the number of states is e to the s, then the trace of -1 to the f is the square root of that. So you can interpret it as kind of having a random distribution between boson and fermion. So maybe that's what I was thinking as the.
But you don't have intuition for this 1/2 from the exponent?
No, I come from the calculation. Yeah. I was just saying that intuition would be that is what you will get if you have a random distribution of signs.
Would it give 1/2 to the exponent?
Yeah, square root of a number of states. Yeah, yeah.
Okay.
And to me this is more satisfactory, but okay, maybe how you should interpret it, maybe that I will leave to, I don't know. Maybe I should focus on that.
This is also, if you do it in ADS, for example, also.
Yeah, so in ADS I get it, that's the next slide.
And that's for far from extremality, also close to extremality?
No, here there is no extremality because there is no charge.
No, but you can, there is an external.
Oh, yes, but I mean, yeah, but this state is dominated by, well, first of all, we're fixing the mass to be anything, so it doesn't, in general, it's not extremal. Yeah.
And the external curve is not supersymmetric.
Yeah. Yes, and in the case, before I move to ADS, well, let me just say because it's quickly, but so in ADS I get that similar answer, but instead of 1/2 is order 1 number, it's more than 1.
Just to check this conjecture that it's just randomly distributed.
No, that's not true. This is, I mean, it's still an order 1 number smaller than 1, but it's not exactly 1/2. That's special of flat space. Yeah. But that's just expectation. I mean, the real conjecture is that if you do this path integral in gravity, it should tell you what's going on with the states in the CFT, and then that you have to check somehow. Okay. Let me mention what would be a naive way of computing this quantity. This is naive because we cannot really trust the from semiclassical gravity. We don't really have access to just such fine-tuned questions about J, because J should be a further 1/G Newton in gravity. But let's imagine we just take the entropy of a curved black hole of mass m and angular momentum J, and we just sum over J, putting that phase by hand. Then we integrate over J's that are smaller than m squared, so we integrate over the geometries that we believe that represent actual states of the system. And if you do this sum and you take the large, small g Newton or the large mass limit, then you do find that it goes as e to the s over 2. But I don't think this calculation is really justified, because I think you're extrapolating the formula to a precision that is not really meant to be applicable. But I just wanted to mention that this works if you do it this way.
Well, if you don't put this constraint on J, do you have something?
Then you don't. Yeah, that's funny.
What do you get in the other case?
Oh, I don't remember.
Are they subleading or they're competing with the
I don't remember.
If it's subleading, that doesn't matter, right?
No, it's not subleading. I think, if I remember correctly, I think it gives a different answer.
It's more leading than you.
Yeah. But I need to check. I don't remember on the top of my head. Okay, like I said, we check other cases, the charged black holes or uncharged, or you can do whatever you want, in black holes in ADS in 4 or more dimensions, and we also check black holes in ADS in 3 dimensions. And by that, what we did is what Ivan was saying, where you put the -1 to the f not with respect to the SU2 charge that comes from the rotation in S3, but with respect to the momentum inside ADS3, and that's not the elliptic genus, it's something else. And quantitatively, the answer always has this form where gamma is some parameter. For example, for an uncharged black hole in ADS4, we get this curve. So if the mass is very small, it goes to 1/2, which is the flat space answer, and if the mass is very large, then it goes to some order 1 number that's smaller than 1/2.
But what is known in general about this? Like not for black holes, but for some quantum systems. Are there some statements what one expects for this gamma to be there?
No, not that I know of. So I think that's, we're just exploring this. Maybe there is. It would be nice to know.
Just follow me.
Right.
Just that, I mean, you can look at examples, but usually if you can solve it, then it's probably not related to black holes. Because probably we pick up some of system. Maybe in SYK one can, oh yeah, we checked SYK, but I don't remember what lens was. Because this is not protected, you really need to solve the theory somehow.
What is the smallest number gamma that you obtained from the example?
So, my next slide, sometimes it's negative. So it means that the black hole doesn't even dominate. So so in ADS5, that happens for large black holes in ADS5. So if you look at the temperature, you have a Hawking phase transition. If you compute the partition function, where below you have thermal ADS and above you have an ADS black hole. But if you compute this index saddle in this case, then above the Hawking phase transition, actually for all temperatures, but in particular above the Hawking phase transition, that gamma is negative. Then the black hole is not dominant and you have thermal ADS. So then that's something one would know how to compute it, check. So even though the partition function will go as e to the n squared, the -1 to the f will go as less than that. I don't know exactly how, because maybe there is a possibility that there might be some kind of defect that will smoothen out this choice of periodicity condition that you can model by saying that it has some tension and then compute the contribution given the tension of that defect. But that's something that you need. It would not be something universal like the black hole. You need to know the details of the theory to see what goes into that defect, and then I don't know if one can construct them in For example, the type 2B example I used to.
Yeah, in the field theory, people have studied those defects that changing the characteristic condition for the fermion. But I don't think
Are
people
they
study
basis
holographic field.
in ADS5?
People studying four-dimensional supersymmetric, supercomplementary.
I see. Yeah, so I would like to do that in the bulk.
Yeah,
Yeah.
but I don't think people have looked at it.
Okay. Okay. Maybe I will ask later if you think there is some way of doing it that way. Okay, so I think that's all. Yeah. Okay. So we show how to compute the partition function with an insertion of -1 to the f using gravity. Well, we applied it to the supersymmetric black holes and non-supersymmetric theories. I mentioned some consequences for holographic CFTs that would be nice to check at some point. And I also wanted to mention another application, which is for small black holes in string theory. So this is something that we are exploring, but I don't have such a final story yet. But there are systems in string theory that strong coupling becomes well, the black hole solution of the would-be black hole has 0 area, so then they are called small black holes because to leading order in the gravity approximation, their area goes to 0. And they are obviously singular, so the event horizon is singular, they're like a naked singularity. But nevertheless, if you ignore this and imagine that the horizon has some order alpha prime size and compute the entropy, you get the right answer. I think this was pointed out by Doublecard. And also, well, originally by Sen, but then more precise by Doublecard, I think. So you could imagine applying it to the small black hole in the sense that maybe this is a pathology of computing the index at 0 temperature. And if you compute the index at finite temperature and you add this rotation, the rotation can smooth out the singularity at the horizon. And then you would be able to put those calculations in more, to make them more rigorous. Okay, that's something that I'm trying to understand. Okay, and then some other future directions. So I think I already mentioned this, but something that we didn't work it out yet, but it's work in progress to extend these Kerr-Newman solutions to the full attractor-like geometries when you have an equals to supergravity coupled to vector multiplex. That appears, for example, if you compactify string theory on caviar or the 4 dimensions. Okay, I already mentioned the small black hole. Okay, that's it. Thank you very much.
Any more questions?
In AS3, you said that you actually use another angular momentum on S3, but could you also use angular momentum on AS3? And if you do that, is that combination of omega and beta corresponding to some special value of the tau of the modular parameter?
Yeah, that's what it is. So in the elliptic genus, that corresponds to a special value of the chemical potential of the SU2 symmetry, and in this case, it corresponds to some particular value of the tau of the boundary.
Related to that, this thing of having negative omega, A gamma.
Yeah.
When you cross the Hawking page.
Yeah.
So in AS3 you also have a Hawking page transition a certain value of parameter. Also you see this in the three-dimensional case?
I don't remember because it's like a case by case, but I think it doesn't happen in ADS3.
Just to know if it is like some
No, I think in ADS3 it doesn't happen. I think it's just that gamma and some order 1 numbers more than 1.
But it's still possible.
Yeah. I can check that.
Okay, if no more questions, then let's start talking again.